Okay, so where does stress concentration occur? Almost anywhere where you can see there is a fixture, an attachment, or there's a change in cross section. So examples of places where there is stress, uh, bolts would have them. That's because bolts have change in cross section area. So like something like this. Okay, so these are the threads. This is the head. And because there's a change in geometry, that's a good candidate for stresses to build up. Again, here there's a change in geometry. Those grooves are not going to be any, there will be problems because of grooves. That's where you'll have stresses. So anywhere there's change in geometry, you would have stress concentration. That is, the stresses would be exceedingly high, and where stresses are exceedingly high, you will see that things will fail. Other places would be transmission shafts. Shafts are very ubiquitous in design. So once you have shafts, you need to secure them. And how you secure them is through keys, keyways, key seat. These are methods of attaching shafts to other things, and they always invariably involve cutting into the shaft, which in turn leads to stress concentration. We can also have shoulders on shaft. Grooves. So these are intentionally cuts made so as to uh, hold other things, notches, etc. will cause stress concentration. Okay, and the stress concentration uh, can be quite high that those parts will fail first. Now, how do we work with stress concentration? Uh, this is how we'll do it. We'll use what is known as stress concentration factors. Okay, these are non-dimensional numbers. I'll call, well, two of them we'll use is KT and KTS. KT is for normal stress. Will be sigma max divided by sigma 0, and I'll define what these are. And then KTS will use for shear stress, tau max divided by tau 0. Okay, now sigma 0, uh, tau 0 are the nominal stresses. In the absence of discontinuity or change in geometry. It's a discontinuity change in geometry. This is the stress you would expect if the material was, if there was no change in geometry, there was no discontinuity. It's the normal stress. It's not that high. But sigma max and tau max are uh, the maximum stresses due to discontinuity or change in geometry. These are the stresses due to stress concentration, in other words. And then KT and KTS are the non-dimensional numbers which are clearly non-dimensional, and they are greater than 1, much greater than 1 actually, and these only depend on geometry. Okay, they do not depend on the material. So what they're saying is if these numbers are greater than 1, that means that if you see these expressions, if kt is greater than 1, kts is greater than 1, then sigma max is greater than sigma 0, which means that that basically tells you something about how severe is the stress concentration. If the value is 10, let's say of kt, then it means that the maximum stress would be 10 times the nominal stress, which is really bad for the design. It's going to fail probably if the loading increases. Now, how do you get kt and kts is well, if you use finite element, it'll actually give you some hints at what kt kts is. That's one way. The other way is to actually create the geometry with the right uh, change in geometry, apply a stress, and basically figure out the stresses by measuring the actual stress. And from that, you can figure out what KT and KTs is. So somebody has done an experiment offline and figured out what KT and KTS is. And as I said, it's only depends on geometry. And what I'm going to do is I've actually put this on Blackboard. This is basically the appendix from the book. You need to go and scroll down to, I think, table 15, 16. Here from A15. Okay, this is something which I posted on in the handout section of Blackboard. You can download it. It's basically the appendix from the book. But table A15 onwards tells you stress concentration factor. For example, here it's given KT for different geometries. So for example, this is a rectangular plate with a hole, and you can see that it has a width W, it has a thickness, well, the diameter of the hole is D, and based on the ratio of uh, D divided by W, you can compute what KT is going to be. Okay, so when this ratio is exceedingly small, okay, that's the hole is relatively very small compared to W, you would have almost close to 0, you have the highest stress concentration. But as the hole becomes bigger and bigger, the stress concentration factor actually decreases. Okay, because for a small hole, the change in geometry is sudden, and as the hole increases in size, the change in geometry is not that sudden. So the KT decreases. However, that does not mean that the stress actually decreases. The stress is a different calculation. You need to first remember that the stress, sigma max, is KT times sigma 0. So the maximum stress depends on KT and sigma 0. So just because KT for this for a small hole is higher than KT due to a bigger hole does not mean that the stress is going to be lower, because it also depends on sigma 0. The stress is also a function of sigma 0. So you'll have to put everything in this equation to figure out what the actual stress is. So then we have the same plate with a hole, but now with a bending moment M. Okay, so that gives you the stress concentration factor for that. This is a plate with a groove like this. Depending on the ratio W divided by D, depending on R divided by D, you can compute what KT is. So you need two non-dimensionless numbers to figure this out. We can keep going. That's the same geometry, but due to M. Here is a different geometry. Here it depends on, well, two numbers, the fillet R divided by D and the ratio of capital D divided by small d. So based on that, you have KT, bending moment, and then let's see. Then you have a circular shaft, but with the fillet. And so again, we have KT for that. Now comes torsion, so that will be KTS. Again, it depends on R divided by D and capital D divided by D due to M. A circular shaft with a hole as shown due to torque, due to moment. This is a square, well, it's a rectangular section, but subjected to force F. Okay, plate loaded in tension by a pin through a hole. So if there's a pin through the hole, I think this is the pin, then this is what you'd expect. So it just keeps going on, but this is something which I'll give you obviously, and you'll use this to solve problems. And